Okay, so yesterday we talked about specific heat capacity, okay? That's that physical property that tells us how quickly something can heat up or cool down, okay? And that was this formula here, E equals m times c times delta t, okay? And for that, obviously, we've got energy, mass, C is specific heat capacity, delta T is change in temperature. Okay, that is a formula that we use when we're doing heating curve or latent heat questions. Okay, second thing we went over, or started to go over, is latent heat. That's what we're going to spend probably 2/3 of today's class working on today. So, there's two types of latent heat. Okay, there's the latent heat that happens when you're changing state between solid and liquid, or liquid back to solid, so melting and freezing. Okay? And there's the latent heat that is involved in changing from liquid to gas, or from gas to liquid. All right? And we were looking at those yesterday, okay? And we said that the formulas you're going to use on this heating curve have to do with the type of thermal energy being changed. Okay? Anytime the line is going up, okay, we're changing the kinetic thermal energy of the material. In this case, it's going to be water. Okay? And then we would use the E equals mc delta T formula. Okay? So right here, when we're heating up the ice, we would use E equals mc delta T, and we would use the specific heat capacity of ice. There. Right here, where we're dealing with heating up water, we would use E equals mc delta T, and we'd be talking about using the specific heat capacity of liquid water. And then up here, when we have steam, if I add energy to steam, steam still gets hotter. Okay? E equals mc delta T, but I use the specific heat capacity for steam. Okay? Now, the problem with these two places where the water changes state is that the temperature doesn't change while that's going on. Okay, it stays flat, as we can see on the graph. We're still putting in energy, but the temperature is not changing. So I can't use this formula, because if I do, it'll tell me there's no change in energy, because I'll get a 0, right? If there's no change in temperature, I'm multiplying something by 0. So we would be using, okay, two different formulas. Okay, one of those formulas, okay, we use between melting and freezing. That's E equals m times the latent heat of fusion. So all the way through this curve, does the mass ever change? No. If I start out with 250 grams of ice, I'm going to have 250 grams of water and 250 grams of steam. I have 250 grams of water no matter what state it's in. I have X number of water molecules. That won't change. Okay, so mass is always going to be the same number all the way through one of these. Okay, and then up here, okay, when I'm boiling off the water and changing it from liquid to gas, then I would use E equals mLV. Okay. Now, LF and LV, I just briefly introduced yesterday. Okay. LF is the latent heat of fusion. It is how much energy is gained or lost when water changes state between between solid and liquid. Okay. And that number is 333 joules per gram. You don't have to memorize that number. It's going to be on your formula sheets on the back of your periodic table. Okay. LV is the latent heat of vaporization. That's 2,260 joules per gram. Right? We were talking about this yesterday, why that means there's so much energy stored in a storm cloud. Okay? And why the water cycle is a big part of transferring energy on a global scale. Every gram of water vapor I should say, that condenses back into liquid water will release this much energy. Okay? And that's a lot. Okay? It's a lot of energy. Okay? If we're talking about thousands and thousands of liters of water, or maybe even millions of liters of water. Okay? It's a lot. It's a lot of energy. Everybody with me there? Okay, let me ask you this. Which would burn you worse? Liquid water boiling at 100 degrees Celsius or steam at 100 degrees Celsius? Why? You're right. Steam will burn you worse. We're told that, right? All our lives when you're cooking something, watch out, steam will burn you really bad. Why?
Because it's like in the air. It's like a lot more like hotter. It's the vaporized water.
Yeah, it's not so much hotter. They're both 100 degrees Celsius, but I get what you're saying with hotter. It has more energy. Look, on this scale here, the x-axis is energy. Water at 100 degrees only has that much energy. Steam at 100 degrees has this much. Is that a lot more? It is, because it takes a lot of energy to turn it from liquid to gas. So it's holding all that latent heat. Okay, that's why I was saying to you, a storm cloud has a lot of energy in it because all the water vapor that's in it is holding all this extra energy. Okay, so if I reach across a kettle and it's just about to boil and throw a bunch of steam out and that steam hits my arm, okay, I'm going to be burned a lot worse than if I spill boiling water on myself. Okay, neither one of those situations is very appealing, but the steam one is way, way worse, right? Because when the steam hits my arm, the first thing it's going to do is condense back into water. And when it does that, it's going to release all the energy the vapor had because it was a vapor and not a liquid. Okay, so that's an extra, what are we looking at there, so an extra 40 kilojoules of energy that it had over the liquid water. Okay, that's a lot. That's why we have to be concerned about steam. Steam has a lot more energy than liquid water. Okay, everybody with me on that idea? Okay, so here's how these problems are going to work. Okay, you're going to get a question and it's going to say, calculate the amount of energy required to heat, let's say, ice at minus 15 to steam at 125. Okay, and what you'll have to do is all of these calculations, right? So you'll have to calculate first how much energy would be needed to heat the ice from minus 15 to 0. Then, how much energy would be required to melt the ice? Then, how much energy would be required to heat the water to boiling? Then, how much energy would be required to evaporate all the water? And then, how much energy would be required to heat the steam? Okay? It's tedious, for sure, but the calculations are easy because all you have to do is plug numbers in. You don't have to manipulate anything, okay? Nothing like that. It's just, okay, I know the mass, I know C, I know the temperature change, you just put the numbers in. Okay, that part of it's really easy. Okay, doing a full question like that with 5 steps is tedious, but each step is easy. Okay, there's no algebra, just plug the numbers in. Everybody with me there? Okay. All right. So when we're talking about the latent heat of fusion, okay, so this was the formula we were talking about here, okay, so to melt 1 gram of ice requires 333 joules worth of energy. It's why we put ice in drinks, okay? They will keep drinks cold because every gram of ice that's going to melt in that drink is going to take 333 joules of energy from the drink or the surroundings or both, okay? Everybody with me on that? So the formula is super easy. Take whatever mass of ice you have and multiply it by 333. Boom, you got your answer. That's how much energy is required. Okay. Right, when we're talking about boiling or condensing, then the number is 2,260 joules. Okay, so to evaporate 1 gram of liquid water into water vapor requires 2,260 joules of energy. Okay, that's why yesterday we were talking about how sweat cools you off. Okay, if you start to perspire, that sweat starts to evaporate. It's going to take 2,260 joules of energy from your body in order to evaporate it. That is going to cool you off quite effectively. Okay, are there ways to make it work better? Like, which way would you feel cooler? Sitting in a chair in the baking sun, okay, sweating, or get up and walk around, or sit in front of a fan? Which one would work best? Sit in front of a fan, because it increases the rate of evaporation. Okay, moving air going by you will increase the rate at which the water evaporates. That's going to allow it to do a better job of cooling you off. Okay, and that's why if you're like super hot, okay, you might feel really good to like splash cold water on your face. Okay, when you splash cold water on your face, okay, it automatically starts to warm up the water. To warm up the water means it's taking energy from you. As that water evaporates, it takes even more energy from you, okay, and you get cooler and cooler. Okay, making sense? Okay, I want you to write this one down. This is going to be an example of the longest kind of latent heat or heating curve question you could get. Okay, I'm going to use this one because I want to demonstrate all the steps at one time. On your exam, don't expect a 5-step question. Okay, I'd probably only give you a 3-step question on this. Okay, give you a minute to write that one down. How do I know on this question that this isn't just one of these? Right, it changes state. Okay, if there's a state change, it's not an E equals MC delta T question alone. It will be part of it, but it's not just a one-step E equals MC delta T question. There's a change in state. That means I'm going to have to do more than this. Okay, so once I've identified that, the next thing I want to do is just draw a rough version of that diagram we had on the board a minute ago. Okay, the heating curve of water. You don't have to make a full graph, just draw the general shape of it. Okay, we know the flat spots on that graph are at 0 and 100. Okay, the reason I want you to draw that is because it'll help you to determine how many and what steps to do. Right? So on this one here, it says we're starting at minus 15 degrees. All right, so that's down here. Okay, at the very bottom of the graph, because that first flat spot is at 0. I'm definitely below that to start. And we're going to 150 degrees. Well, this flat spot is 100, so 150 would be up there somewhere. Everywhere the line changes direction is the end of one step and the start of the next. Okay, so in this one here, if I'm talking my way through it, I start out with ice at minus 15. If I add heat to it, what's it going to do? Not yet. First it has to warm up. It's got to get to 0 before it melts. So that would be from here to here. That would be step 1. Okay, so right below that, I'm going to write step 1. Is the temperature changing in that step? It is. Going from minus 15 to 0. What formula do I use to calculate how much energy that will require? MC delta T, right? All right, so in step 1, I'm going to use that formula. All right. Once I get to 0 degrees Celsius, if I keep adding heat, according to this graph, the temperature isn't going to change, but the ice is going to melt. Okay, what formula will tell me how much energy is required to melt a given mass of ice? Somebody whispered it. E equals M times L F. All right, that's step 2. Okay, and you can just remember, F goes with freezing. Okay, F goes at the freezing point. Okay, at the end of this step, I have water at 0 degrees Celsius. If I keep adding heat, the water is going to heat up until it gets to what temperature? 100. Okay, so it's going to go from 0 to 100. That sounds like a temperature change to me. What formula do I use for that step? MC delta T, right. All right, that's going to be step 3. All right, at the end of step 3, I have boiling water at 100 degrees Celsius. If I keep adding heat, all the water is gonna do is boil until it all turns into vapor. Right, so that is this step here. Since there's no temperature change, I can't use E equals mc delta T. So what formula do I use? E equals mLV this time, because now I'm vaporizing, V for vaporizing the water, right? So that's going to be step 4. Okay, at the end of that step, I've got vapor or steam at 100 degrees Celsius. If I keep adding heat, what's it going to do? If I keep adding heat to steam, it'll get hotter, yeah. Will its temperature change from 100 to 150? Okay, what formula do I use for that? mc delta T, right. Anywhere the temperature changes, that's my formula. Okay, so now I know what formula I'm using in each step. And I've already told you, you're not going to have to manipulate that formula. All you have to do is plug in the correct numbers. All right, let's go back to step 1. So my mass is 250 grams. All right, so E is going to equal 250 grams times, what specific heat capacity should I use? Ice. Okay, remember, water's weird. It has a different specific heat capacity based on whatever state it's in. So I have to use the specific heat capacity for ice, which is on that sheet I gave you the other day. Okay, 2.116 joules per gram degree Celsius. All right, and how much am I changing the temperature of the ice by? 15 degrees. Guys, that right there is the most common mistake people make. A lot of times what I will see here is people will write 165 degrees because they're going from minus 15 to 150. Here's what they forget. It's not ice after 0. This heat capacity only applies while it's ice. So it only applies until it gets to 0. Okay, so my temperature change here is 15 degrees. All right, step 2. Mass still 250? I can put that in for every single one. 250 grams times LF, which is 333 joules per gram. Okay, LF is always that number. It'll never be anything else. Okay, in step 3, I still have 250 grams of water, but now it's actually water, okay, liquid water. So, what specific heat capacity do I use? The one for water, that's 4.2 joules per gram degree Celsius. Okay, what's the temperature change in step 3? 100 degrees, going from 0 to 100. By 100. Okay, in step 4, I still have 250 grams of water, but now I'm vaporizing it. So now I use LV. LV is 2,260 joules per gram. Okay, and then in step 5, still have 250 grams. Now it's steam, so I use the specific heat capacity of steam, 2.02. Okay, and how much am I changing the temperature of the steam by? 50. I'm going from 100 to 150. So the temperature change is 50. Okay, now I know you haven't seen one like that before, but did we do any really challenging math to arrive at these numbers? Most of the numbers we just read off of our sheet. Okay, and we had to calculate some temperature changes. So we had to go 15 minus 0, 100 minus 0, and 150 minus 100. Okay, like there's no challenging math there. All right, so now it's just a matter of plugging these all into our calculators. Okay, so for step 1, 250 times 2.116 times 15 degrees. All right, so that step requires 7,935 joules. Okay, with me so far? All right, then how much energy is required to melt it? So 250 times 333. Okay, is it a lot more? It is. Changing state usually requires more energy than changing temperature. Okay, you're pulling the molecules apart. That takes a lot of energy. So 83,250 joules. All right, then we've got to heat up the water. So we're just punching in our numbers again. 250 times 4.2 times 100. So we're changing the temperature quite a lot. 100 degrees is a lot. So that's going to require a lot of energy. 105,000 joules. Okay. Step 4 is going to be the big one. This is going to require a lot of energy. Okay, 250 times 2,260. $565,000 joules. Okay, 250 grams is 1 cup. Okay, so if you've ever done any cooking, okay, 1 cup is not a lot of water. All right, that's less than the amount of liquid in a can of pop. Okay, a can of pop is 355. Okay, we're talking 250, so a lot less. This is not a lot of water. 565,000 joules. Okay, so obviously that is the biggest part. It's more than all the other parts so far combined. Hello? Hello? Okay. 250 times 2.02 times 50. 25,250 joules. Okay, what do I do with all those numbers I just calculated? Add them all up, right? The question wanted to know how much energy is required to do all of this. Okay, so I take all of those numbers and I add them together. Okay, so I add all those together, 786,435 joules. Was evaporating the water the biggest part of that? Yeah. It was 565,000 of the 786,000. Okay? And that fits with what we saw on that graph. That was by far the longest part of the graph as well. Okay? It's the most energy demanding part. Okay? And again, that goes back to why the water cycle is such a big part of transferring energy. Okay, everybody follow on that one? Okay, so on an exam, I would probably not make you do a 5-step question because it's the same thing a bunch of times. So I would probably ask you to do a 3-step question. So that would probably involve 2 temperature changes and 1 state change. So I might say, you start out with ice at -20 and you want to go to water at 60. Okay, so then you would go, all right, I'm starting here, but I'm ending here this time. How many steps would that be? I just said it a minute ago. 3, yeah, it would be 3 steps. I got to heat the ice, got to melt the ice, got to heat the water, and I stop at 60 degrees Celsius. Okay, if I said take water at 10 degrees Celsius and go to steam at 180, that would be 3 steps. I'd be starting right here and ending way up here somewhere, okay? 3 steps. Right? You put in the formulas, plug in the numbers, add them all together at the end, and you're done. Okay? Everybody with me on how that works? Okay, we're gonna try a few, just practice a few here so you kind of get the hang of it, but I mean, this is probably the most patterned of any of the algebra, well, it's not even really algebra, the math stuff that we do, okay, in this course. Right, as long as you can remember that ice melts at 0 and water boils at 100, you can draw this picture and do these questions. Okay? Okay. Let's have you guys try number 1 there. Okay, so in case you're having trouble reading it from the back, it's 400 grams of water, and you're going from 3 degrees Celsius to 115 degrees Celsius. Okay, answers there in bold at the end, so you can check it when you're done. I'm going to give you a few minutes to try that one on your own, then we'll walk through it together. If you get that one done, go right ahead and try number 2. So, as we said, okay, we know this is not just an E equals mc delta T question because the water changes state, okay, from liquid to gas, so it's not going to be a one-step thing. Okay, here's my heating curve of water. I'm starting at 3 degrees Celsius and I'm going to 115 degrees Celsius, right? So that means I first have to heat the water to 100 degrees, then I got to boil off all the water, and then I have to heat the steam. So there are 3 steps here. Okay, step 1 is a change in temperature, so E equals mc delta T. Step 2 is a change in state from liquid to gas, so that's mLV. And step 3 is again a change in temperature, so that will be E equals mc delta T. Okay, so if I was marking this on a test, I would first give you a mark for the heating curve picture. So make sure you draw that. All right. Then I would give you 2 marks for each step. Okay, 1 mark for picking the right formula and 1 mark for doing the math right. Okay, so in this one here, we are talking about 400 grams times, because it's water, 4.2 joules per gram degree Celsius, and I'm changing it from 3 to 100, so my temperature change is 97. Okay. So for this one here, still 400 grams, but now times LV, 2,260. And for step 3, still 400 grams, but now it's steam, so 2.02. And we're changing it from 100 to 115, so we're only looking at a 15-degree temperature change. Okay, so putting all this in, we got 400 times 4.2, okay, times 97. So that one's 162,960 joules. Then 400 times 2260, okay, 904,000 joules. And then for the last one, 400 times 2.02, whoop, 0.02, okay, times 15 degrees. So that's only 12,120. Okay, so like I said, you'd get 2 marks for each step, provided you did them right. Okay, if you made a mistake but you had the right formula, then you get 1 mark for that step. And then your last mark is for the correct total, which just means add those 3 numbers together. Okay, so that one plus that one plus that one. So we're looking at 1,079,080 joules. Okay. It's a lot of energy. There's a lot of water, right? It's almost twice as much water as we had before. Okay. Questions on number one? Okay, keep going. I'd like you to do 2 and 3. Okay, so if you're already working on 2, great. Okay, if you're done number 2, then work on number 3. Okay, we'll see where we're at after that. Yep. So for number 2 here, okay, we're asking how much energy would be required to warm, well, it's going to be 1,500 grams, right, 1,500 grams of ice from -17 into steam at 100. Okay, so this one's a little bit tricky in terms of where the steps go. Obviously, I'm starting down here at -17, but I'm only going to here. Steam at 100. I'm not heating the steam. Okay, the steam, I'm just going to boil off the water. I'm going to end right here because this is 100 degrees. This would be steam at 100. So that's going to be 1, 2, 3, 4 steps. Okay, so the first thing I have to do, I have to heat up the ice. Then I got to melt the ice. Okay, then I've got to heat the water. Then I've got to evaporate the water. Okay, those are my 4 steps. Right, that's why it's really important to know that 0 and that 100 point. If it says steam at 100, steam exists at 100, but I didn't have to do anything other than evaporate the water to get it. Okay, so for this one here, okay, we'll have 1,500 times 2.116, okay, times 17 degrees, because we're taking it from -17 to 0. Okay, this here will be 1,500 times 333. Okay, this one here will be 1,500 times 4.2, because it's water, times the full 100 degrees. We're going from 0 to 100. And then here, 1,500 times 2,260. Okay, if we put all that together, it's a lot of energy. 4.5 million joules. Okay, everybody with me there? Okay, how many people found that one a little bit tricky? Okay, and that's okay, but just know that that's also the kind of thing I could ask, right? It's knowing where to stop and end each step that's super important there. All right, how many people are done number 3? Okay, I'm going to give you, what do we got here? Give you about another 4 minutes to finish up number 3, and then we'll go through it, and then we're going to move on.
When I put my numbers in the calculator for number 2, I'm not getting that answer.
Okay, let me just double check the math here, yeah? Yeah, you're right. I'm not getting that number either. Are you getting 500 or 5.2 million instead?
I'm getting 4.2.
Oh, I see what happened here. I put in a plus there. I made a mistake. I put in a plus here, which I should not have done. So let's try that again. Because that number there is way too big. Okay, let's do this. Back up to the top here. Okay, so we want that number plus that number, that number, and then this number here, 1,500 times 2260. No, it is that number. way too big.
Oh, yeah.
Okay, so, okay, how many people are not getting that number? 'Cause now I've got it again here. Okay, so guys, it's gotta be an entry thing, okay? Make sure you're using the correct specific heat capacity for ice, correct specific heat capacity for water, and that you're using 1,500 grams, okay, in here, right? This is 17, make sure you're only using 17 degrees, 100 degrees, okay? I can do it one more time here, but I'm pretty sure I'll get the same answer. 1,500 times 2.116 times 17 plus 1,500 times 333 plus 1,500 times 4.2 times 100, okay, plus 1,500 times 2,260. Yeah. So it's got to be an entry thing somewhere, guys. Yeah, sleep phone. Okay, so just kind of double check the entry in your calculator, but okay, I've done it a bunch of different times now and I'm getting that same answer, so. Okay, keep working on number 3 there, guys. Okay, like I said, I'll give you a couple more minutes here on number 3 and then we'll go through it and then we're gonna move on to biomes here. Okay, guys, let's walk through number 3 here. Okay, so we draw our heating curve. Okay, and this one starts as steam. So we're starting up here at 135 and we're going to water at 12. Doesn't really change anything, okay? My first step will just be steam, okay? The same amount of energy is required or is given off in cooling as is required to get it there in heating. It doesn't change at all what we do. I mean, technically, the answer could be negative because it does represent a loss of energy, but because the question says released, you don't have to put that on there. It's already established that this is energy that's being lost. Okay, so we're starting up here, we gotta cool the steam down to 100. When it gets to 100, it's gonna condense into liquid water and release all of its latent heat, and then it will cool down from 100 down to 12. So that's step 1, that's step 2, and that is step 3. All right, so for step 1, okay, it's changing temperature, so that's an E equals MC delta T calculation. Step 2, we're condensing the steam, so that's E equals MLV. And in step 3, we're cooling the water, so that's a change in temperature, so that's E equals MC delta T. Now it's just a matter of plugging in our numbers here. We have 250 grams, so 250 times 2.02. Okay, times 35 degrees, because we're cooling from 135 to 100. And then that will be 250 times 2.02 times 35. So that is 17,675 joules. Okay, and then how much energy is released when it condenses? That's going to be 250 times 2260. All right, so 565,000 joules. Okay, so that's 250 times 2260. And then this is going to be 250 times 4.2 times 88 degrees, because we're going from 100 down to 12. Okay, so 250 times 4.2 times 88. All right, so 92,400. Then we just put those 3 numbers together. Okay, so we're looking at 675,075 joules, which is exactly what we got there. Yeah, just leave your phone. All right, questions on that one? Are they all pretty patterned? Okay, now, in the workbook that I put on Google Classroom, there is another sheet full of these, and we didn't do all the ones on this sheet either, okay? There. Okay, so there's a whole bunch here. Answers are on that sheet, so if you want to try a few of those at home, it's probably not a bad idea. Okay, to do that as a way of studying for Thursday's unit exam. There will be one of these on the unit exam. Is it important to show your work on all the steps?
Yes.
Yes. Okay, if you accidentally mess up punching something into your calculator, this is an 8-mark question. Okay, if I give you a 3-step question, I am, okay, it's an 8-mark question. And you want to show all your work just in case you mess up on the calculator. Alrighty. Alright, so this should seem at least somewhat familiar to you because you do go over biomes and ecosystems. I believe it's in like grade 8. Okay, so some of these are going to sound or at least look familiar. Here's what you're going to be asked to do with the information that's in this lesson on your unit exam and on the final. There will be multiple choice questions that give you a picture and a description of a biome, and you're going to have to pick the right one. Okay, so if I gave you a question that said, these are like dense, thick forests that don't lose their leaves and exist near the equator and have very heavy rainfall and even temperatures, and your options were A, desert, B, tundra, C, boreal forest, and D, tropical rainforest, you'd probably be able to pick out that it was a tropical rainforest, okay? Like, it's gonna be that simple, really, okay? So there'll be a number of multiple choice questions that just require you to look at a picture, read a description, and pick the right biome. Caution, don't just look at the picture, okay? Read the description as well. Some biomes have areas of overlap. Okay, sometimes a picture can be a little bit misleading. The picture is there to support the description. It is not worth 1,000 words. Okay, I don't know where that saying comes from, but it's not true. Okay, a picture is not worth 1,000 words. Make sure you read the description as well. Okay, and then the second thing you're going to be required to do is, I show you a climate graph. Okay, we talked about those the other day. You're going to see them in the notes here. Okay, you be able to look at a climate graph and tell me what biome it comes from and why. Okay, everybody with me there? So that's the only 2 things you have to do with the information in this lesson. All right. Okay, so biomes are ecological regions that exist on Earth. They have very distinctive flora and fauna, that's plants and animals, right? They have those plants and animals because the plants and animals that live there are influenced by the climate of that particular area. Okay? It's why you can kind of see patterns to the colors on this map. Okay? So for example, dark green is a tropical rainforest. Okay? Tropical rainforests all basically exist near the equator. Okay? You don't really see any tropical rainforests outside of 30 degrees north or south of the equator. Okay? It is a tropical biome. Okay? Same with, like if we look at coniferous forest, that's the boreal forest. Okay? So that would be this kind of aquamarine color here. Okay? You see that in North America, you see it in Asia, right? And you see it on mountain ranges. Okay, which would all have colder temperatures because of either a really high latitude or a really high altitude. Either one, we know, makes an effect on temperature. Okay, everyone following me there? So there's patterns to all of these. Okay, so for the tropical rainforest, you see that mostly near the equator. Okay, obviously you've got the big old Amazon rainforest here in South America. Okay, you've got rainforests in parts of Africa, Madagascar, and Southeast Asia. Okay, so that would be like southern China, Vietnam, Laos, the Philippines, Papua New Guinea, all of that is all, okay, tropical rainforest. Okay, very equatorial. So like a dead flat temperature line on a climate graph. Okay, then we would see savanna. Okay, savanna would be what you would associate in your mind with Central Africa. Okay, so lions, tigers, not bears. Okay, giraffes, elephants, wildebeests, things like that. Okay, the open kind of safari kind of thing that you would associate. And that's why you see savanna is mostly in Africa, okay? But there are little patches of it in other areas, and those areas are also fairly tropical. Okay? The savanna is really a tropical grassland, okay? So not a forest, but a grassland. Deserts. There's different kinds of deserts. Okay? There's hot deserts, and then there's hot, dry deserts, and then there's just dry deserts. Okay? So if we're looking here, obviously, okay, for desert, yeah, northern Africa, so okay, like, you know, Egypt, Tunisia, Morocco, okay, all of the Middle East, okay, all of those kind of things. That's obviously the big shifting sand dunes, okay, of the Sahara that you would, you know, picture in your mind. But there's also desert in North America. Okay, this would be like Southern California, Arizona, Nevada, maybe even parts of Utah, okay, Baja in Mexico, okay. There's the central part of Australia is all desert, okay, and right here, okay, these are the Himalayas right here, right, this thing right here, okay, this is the Gobi Desert. It's a rain shadow. Okay? You can clearly see it's right behind a set of mountains. Okay? That's a rain shadow desert. Okay? But this is a cold desert, where this is a hot desert. Okay? The one thing that all deserts have in common, they're dry. Okay? That's the main thing. All right? Obviously up here, okay, in Arizona, yeah, sure, in the summertime, Arizona is punishingly hot. But they get snow in Arizona too. Okay? It's a mid-latitude desert. What does it have in common with the Sahara? It's dry. Okay? But they look different. Okay? All deserts have in common is they're dry. Okay, chaparral. Chaparral is also sometimes called the Mediterranean climate, okay, or a scleriferous forest biome. Okay, that would be the Mediterranean, hence the name Mediterranean climate. Okay, so you see like you know, parts of like Italy and Greece and things like that. So around the Mediterranean, that's where you're going to see things like olives and palms and things like that. Okay, Southern California, okay, or Central California maybe, okay, is also kind of like that. Okay, you see a little bit here in South Africa, a little bit on the tip of Australia there, but that is pretty much entirely based in Southern Europe, very northwestern Africa. Okay, oceans, yeah. They're full of water. We don't really talk about those. We're going to talk about the terrestrial biomes only. Okay? Temperate deciduous forest. Deciduous means the trees do what? Every winter they shed their leaves, exactly. Okay? Which is, of course, why you see most of the eastern seaboard of the United States and southern parts of Ontario, Quebec, okay? Things like that, even maybe a little bit of Manitoba, and some of the Maritimes are all that color. All right, that's maple trees, okay, things like that. They lose their leaves every year. Okay, much of Europe is also that biome. Okay, coniferous forest, like we said, that's the boreal forest. So much of Canada, northern Canada at least. Okay, so northern Alberta, northern Saskatchewan, northern Manitoba, Yukon, Northwest Territories, Nunavut. Okay, all of those places, lots of Quebec. Okay, are going to be boreal forest. Most of Russia, okay, is going to be boreal forest as well. The tundra, so the tundra is even further north than the boreal forest. Okay? The tundra is an Arctic grassland. Okay? So we're missing one here. Oh, I skipped it. Never mind. Okay, so the tundra is an Arctic grassland. It's really, really cold. Okay, it's too cold for trees to grow. Okay, so that would be the very northern parts of Canada, Siberia, okay, the very northern parts of Russia, little edges of Greenland, Iceland. Okay, things like that. And then polar and high mountain ice. This is also sometimes called the like cold deserts. Okay? Antarctica, driest continent on Earth. Okay? It is a polar or cold desert. Okay? Tops of mountain ranges, Greenland, okay? Those are polar deserts. The one I skipped, oddly enough, is the one we live in. The prairies, or temperate grassland. Okay? Temperate means not near the pole, but also not close to the equator, right smack in the middle. Okay, so temperate would generally go from like the tropics, okay, like the end of the tropics to about like, let's say 60 degrees north or so. That would be temperate. Okay, so you can see here, these are the Rockies right here. The prairies are a rain shadow of the Rockies. Okay, much of like southern Europe and parts of southern Asia. Okay, the Ukraine is part of this. Okay, temperate grasslands. Okay, those are like the breadbasket of the world. That's where the bulk of the agriculture goes on. Okay, questions on where everything is? Okay, so we're going to kind of go into detail here about each and every biome. We probably will only get one done today, and then we'll get the rest done tomorrow and do a quick review for the unit exam. Okay. All right, so we'll start at the equator. Tropical rainforest. How many people have ever been to a place where there's tropical rainforest? Okay, it is so very different than forests in Canada. Okay, if you stand in a forest in Canada, you can see through the trees. Okay, there's wide spaces. There's not a lot of undergrowth. Okay, it's very, very different. You go to the tropical rainforest, and if you are claustrophobic, you will not have fun. Okay, it is oppressive and it closes in. It's very, very dense, very different than anything that you see here in Canada. Okay, now this is just showing like a drone shot of the canopy. Okay, the very upper layer of the tropical rainforest is called the canopy. There are layers upon layers of vegetation from the canopy down to ground level. Okay, it's just a very complex, okay, and diverse biome. Right? Now, this is obviously an equatorial biome. It requires constant rainfall. It requires constant temperatures. So when you look at a climate graph of this biome, you are going to see a flat temperature line. And you are going to see a relatively even and very high level of precipitation. Okay, we're looking at this here, like the wettest month is 225 millimeters of rain, and the driest month is probably 160. Okay, that is torrential rain. Okay, if we got 250 millimeters of rain in a month here, you'd better build an ark. Okay, that's how flooded it would be here if we got that kind of rainfall. Okay, that would make 2013 look like a drought. Okay, we got 75 millimeters of rain or something like that in a week. Okay, and that's what happened. Now, that combined obviously with runoff, so it was a little different. Okay, so looking at a tropical rainforest, it is just a carpet of trees. Okay, like you can't see to the ground. Okay, this river here, we're only seeing part of it. The river probably is more like this. Okay, like it's way wider than the part that we can see. Tropical rainforests are often flooded. Okay, the trees go right out of the floodwater. Okay, this is another example, okay, of just how dense the vegetation is. Okay, this is in Hawaii, and you can see that even the straight up and down, the vertical faces of those mountains have stuff growing on them. You'd never see that here. Okay, the vertical parts of mountains don't have anything growing on them because they're dry and they don't hold any water. Here it rains so much that plants can grow on anything like a chia pet. Okay, you guys have ever seen one of those, right? Like they're like the porcelain or pottery things, and you put the seeds on them and it'll grow all over them. Okay, so just super dense vegetation. Okay, so general characteristics. Okay, I'm not worried. You're never going to need to know that 13% number. I'm never going to ask you that. Okay, they're complex. They're variable. There's no seasons, right? There's no summer, winter, fall, or spring. There's all the time. Okay, hot and wet. Okay, muggy, lots of precipitation, okay, very even all year long. Okay, now soils in the rainforest, believe it or not, are very, very poor. Okay, and that's because most of the time they're flooded. So all the nutrients get leached out of them. Okay, and that process is exactly what it sounds like. Okay, a leech sucks your blood. Okay, leaching, the floodwaters pull all the nutrients and things like that out of the soil because of diffusion. The floodwaters don't have any nutrients in them. The soil, they're sitting on top of the soil that does. Everything naturally moves from high concentration to low concentration. Okay, the floodwaters literally suck all the nutrients right out of the dirt. This is why agriculture is really hard in these areas. Okay, people, because they're poor and they're starving, will do slash and burn agriculture. They'll just cut down the forest, burn it, and try and grow crops. that might work for 1 or 2 seasons before the soil just craps out. Okay, it just doesn't have enough nutrients in it to support any kind of agriculture. Really, really difficult, okay, to grow your own food in a place like that. Okay, decomposition is very fast. Hot temperatures, okay, lots of moisture, that is a recipe for things decomposing very, very quickly. So nutrients get cycled fast. They just don't stay where they need to be. They get washed away. Okay, so there's almost no aid horizon. Okay, if we're talking about those soil horizons we talked about before, tropical rainforests have virtually no topsoil. Okay, it just gets washed away and eroded all the time by all the torrential rain. Okay, so that's what a soil profile would look like. Okay, very little aid horizon. Clay doesn't wash away very easily, so you'd have a pretty thick B horizon full of clay, and the parent material would be quite deep down below that. All right, now for vegetation. Okay, so you can see the different layers there on that picture on the right. So you got ground level, okay, you've got those buttress or snorkel roots that a lot of the taller trees will have to keep out of the floodwaters. You got your shrub layer, so low plants, okay, then you've got your under canopy, your main canopy, your emergence. In some tropical rainforests there can be 5 or 6 different layers of vegetation, okay. The forests are also very diverse. If you go into Kananaskis or Banff or something like that, you're going to see Douglas fir, lodgepole pine, white spruce, black spruce, poplar. You're going to see 5 different kinds of trees. In a tropical rainforest, there can be up to 100 different types of trees in an area that would be equal to what's enclosed by the running track out back. Okay? In a Canadian forest, there might be 100 trees, period, in that area, but they'd all be of 5 types, probably 3 types. Okay? But in a tropical rainforest, that area could have thousands of trees, and there could be 100 different kinds. Okay? So it's very, very diverse. It's very different than what we see here. Okay? This is a picture that I took when I went walking into the rainforest, which was a huge mistake, because I didn't have any of my usual hiking gear. Mostly my concern would be the lack of my machete. Okay, I walked in here and the forest just closed in behind me. It's very disorienting. Here in Canada, you walk into the forest, you can still usually see the sun. You've got reference points where, okay, there's a river there or something like that. You can see a ways, you can't hear. You get closed in, it's so thick, it's so tall, you can't see the sun, you have no idea which way you're walking. Okay, and I got turned around and I got lost. Okay, I just happened to get lucky that at one point I got close enough to a road that I could hear. Okay, and then I was able to walk towards the sound that I could hear and end up on the road. Okay, I ended up like 4 kilometers from where I started. I had no idea where I was because I had no ability to navigate. Okay, so if you walk into the rainforest, carry a machete. That's one of those big knives, made about this long. Okay, and swing it and make a path of destruction that you can follow back like breadcrumbs. That's the only way you navigate, okay, in a tropical rainforest. Okay, so very, very thick. Okay, very, very different than what we see here. Okay, in terms of animals, so that was the flora. This is the fauna. You know how you've heard that saying that the lion is the king of the jungle? Guess where lions don't live? The jungle. Yeah, they don't live in the tropical rainforest. They live in the savanna. Okay? Large predators are not present in the rainforest. In fact, there are very few large animals in the rainforest because you can't live on the ground. It's flooded all the time. Most of the animals live in the trees, and most of them are amphibians or bugs. If you don't like bugs, don't take a holiday to the tropical rainforest. You won't have fun. Bugs are everywhere. And some of them are really big and gross and scary. Okay? Like, you know, the praying mantis, which eats other bugs. Okay? The walking stick, they're not too scary, but they're weird looking. Okay? Or the dung beetle, whose mating ritual is to make a big ball of their own poop to impress their prospective mates. Guys, that is not going to work for you. Do not make a pile of poop. The girls will not be impressed. Okay, but for bugs, it apparently is really cool. Yeah. Okay, so lots of different kinds of bugs. Very few mammals. and they're all really small rodents, okay? And lots of amphibians, frogs, things like that. Also, the more brightly colored the amphibian is, the more poisonous it is. Don't lick the frogs. You may see colors, but it might also be the last thing you see, okay? Because they're, yeah. And gross, it's a frog. You get salmonella. Yeah, don't do that. Okay, we will leave it there for today, and we'll continue there and do our review tomorrow.